In this video, we're going to discuss the Brinell Hardness test, which is used to determine the indentation hardness of different materials. Now, if we refer to our diagram in the top left corner, we have the surface of a given material, here highlighted in blue, and we want to determine the indentation hardness of that surface. Now, during this test, we have a circular indenter, which is placed on the surface, and then we apply a force F to the indenter such that it will leave an indentation in the surface of the material. So it's a relatively straightforward test, but what we need to be able to do is interpret the results from the test in order to find the Brinell hardness. And Brinell hardness is a standard measure of hardness across the industry. If we know the Brinell hardness of different materials, we can determine their resistance to scratching and indentation. So directly under the diagram, I have the formula that's used for calculating Brinell hardness, and we have various different terms in that formula. On the top of the fraction we have F, which is the applied force. Now typically for a Brinell hardness test, the force will be 3,000, but it will be 3,000 kilograms of force. Now we can easily convert that into newtons just by multiplying that by gravity. So we have F equals 3,000 times gravity. We know that gravity is 9.81, therefore the force 3,000 times 9.81 equals 29430 newtons. So typically in a Brinell test, we're applying 29430 newtons worth of force. Now another standard for the Brinell hardness test is that the indenter is generally made from steel. Now if we're testing the hardness of harder materials, then we can use a tungsten carbide indenter, but generally the material is steel. And normally the diameter of the indenter is 10 millimeters. Now we can leave that diameter in millimeters because if we refer to our equation in the bottom left hand corner, we actually need the diameter of the indenter in millimeters. Now let's take an example. Let's assume we're trying to find the Brinell hardness of mild steel, and we conduct the test using a 10 mm steel indenter and applying a force of 3,000 kilograms of force, or 29430 newtons. And when we've conducted the test, we measure the diameter of the indentation. The diameter of the indentation is lowercase d, and it will be the diameter of the indentation that's left in the surface of the material. Let's assume that we measure that and it comes out as 5.3 millimeters. Now we can apply the formula for the Brinell hardness number in order to determine the Brinell hardness of the surface of our mild steel. And that will give us a point of comparison for other materials. So let's do that calculation now. We have Brinell hardness number equals 2 times the force in newtons, so 2 times 29430, all divided by pi times the diameter times gravity. Well, the diameter needs to be expressed in millimeters, and gravity is 9.81. Then inside the brackets, we have the diameter in millimeters again, 10, minus the square root of 10 squared minus the diameter of the indentation in millimeters squared, so minus 5.3 squared. Just note that it's all of 10 squared minus 5.3 squared that we're square rooting. So if we close the brackets and then run all of that through our calculators, we get a Brinell hardness number equal to 125.6 HB. For Brinell hardness. So to summarise, we have a number of different standards for this test. We use a standard force of 300 kilograms of force, and we use a standard 10 mm steel indenter. We place the steel indenter on the material and apply the force, and after the force has been applied, we measure the size of the indentation. So in actual fact, the only thing that changes in our Brinell hardness number formula here is the diameter of the indentation, and that will be dependent on the material. When we take the determined value of the diameter of the indentation, we can apply that into our Brinell hardness number formula, and as a result we get a standard Brinell hardness number for the material being tested. Now, it is important to note that we can only carry out this test if we're able to remove the material from service. And in the next video, we'll look at an alternative method using a portable hardness tester, which can be used if the component or material is still in service.